You want to begin at the beginning here?
Yeah, that's the one I went through recently.
Yeah, we've gone through some of these problems, I noticed.
Yeah.
I noticed the way you did the first one was you applied L'Hopital's rule.
Yeah.
That was pretty clever. But you're not supposed to know L'Hopital's rule yet. So they may want you to do this in a more normal way.
Well, originally I had done it that way, but took this test twice because the first paper I dropped in the snow and the ink bled.
Okay.
So when I went back to do it a second time so I could still show my work, I just did it the faster way.
Okay.
Since I was running low on time.
Yeah, notice that that's the same problem as this.
Yeah.
And if we factor the top, now we can cancel out that from the bottom, and it's x plus 1. So if x is going to 1, you just substitute it in and it goes to 2. All right, 2, just the ratio of the coefficients of the highest degree polynomial when x is going to infinity. That's correct. 3. The first thing, since 3 can't be factored, I mean the numerator can be factored, but the denominator can't be.
Yeah.
So let's just plug it in to see what we get for starters. Well, when you plug in x goes to 2, you get 0 over 8.
Mm-hmm.
Well, the limit of 0 over any number is 0.
Yeah, I guess I made a mistake there. Didn't even try that.
Okay. Yeah, normally these are difficult because it's always 0 over 0, and those are the hard ones. But anything that is 0 over a number goes to 0, and anything that is a number over 0 goes to infinity.
I guess that's what happens when you try taking a test in a hurry. You don't bother checking the easy thing.
Right. Okay. Yeah, that one looks right. That one looks right.
And then 6 we did together.
6 we did together. Setting that equal to that, and then filling in 3 for x and solving for c. I can't read your writing here, but the only thing we really need to do to prove that it is continuous at -3 is to see if both of those functions are equal to the same thing at -3. And one is equal to 22 and the other is equal to 22. So regardless of what it looks like to the left, I mean that's continuous except at that point. So as long as they're equal to one another at -3, to me that proves continuity.
Okay.
Okay. You need to go through any of these?
No, that was...
Yeah. This one, a little different.
That one
The domain of f. Well, what's our only restriction here?
That you can't have a 0 in the denominator.
Or you can't have what's inside that radical be negative.
Oh, yeah.
In other words, x can't be 1. Right? Because then you're taking the square root of it. So the way to solve this is to say that whatever's inside the radical has to be greater than 0. Can't even be equal to 0. Okay, now if we solve this inequality, we get x squared has to be greater than 4, And now if we take the square root of both sides, we get x has to be greater than 2, and the other half of that square root, you switch the inequality sign, and x has to be less than minus 2. In other words, x cannot be between minus 2 and 2, or you will violate the domains. So x would, you use interval notation, right?
Yeah.
So in other words, that's going to be negative infinity to minus 2 combined with 2 to infinity. Parentheses there, because we can't even have that to be 0. Write an equation for each vertical asymptote. Well, if we plotted this thing, and we know x cannot be between 0 or minus 2 and 2, then there's going to have to be asymptotes at each of those. In other words, there's going to be a vertical asymptote at 2 and at plus 2. And the function will not exist in between there. It'll do something, oh, I don't know, like that, maybe. It's going to be hyperbolic in nature, but it will not exist in between minus 2 and 2. But anyway, the equations for the vertical asymptotes are merely x equal minus 2 and x equal 2. Write an equation for each horizontal asymptote. Well, this gets a little tricky, but we can essentially say that we're looking at x over x, right? In other words, we can't actually take the square root of x squared minus 4, but we know that when we take the square root of the x squared part, we're going to have x. So if you look at the leading coefficients of your highest degree polynomial, it's 1 over 1. So there should be a horizontal asymptote at y equal 1. Now, let's just graph this thing. For the heck of it. X divided by quantity x squared minus 4 . That's not what I wanted, is it? The beauty about Wolfram Alpha is it tells you what you put in, and it allows you to correct it.
Fairly easily. Fairly easily correct it.
Yeah, much easier than you can on your calculator. Your calculator doesn't give you this nice feedback here, the input. So if we look at this, the blue is the real part of this function, and the orange is the imaginary part. Now, interesting that they show this blue line here. Not sure what that purpose of showing that line is, or why they put it in blue. Clearly, x cannot be 2. If x were 2, we would have 2 over 0. So this looks right. And there's nothing in between here. And it is hyperbolic in nature. Now, I don't see a horizontal asymptote here. Why is there no horizontal asymptote? Oh, it looks like the horizontal asymptote is at +1 and -1. Why would we have a horizontal asymptote at both places? I guess because when you take the square root of x squared, you really get plus or minus x. So if I'm looking at the coefficients, it's really 1 and -1. So I do have two horizontal asymptotes, y equal +1 and y equal -1. In the same way that if I gave you this function, that is going to have a horizontal asymptote at +1 and -1. Because if I solve this, I get x over plus or minus x. And now if I look at my coefficients, one is +1, the other is -1.
Yeah.
So that needs to be considered when you're taking the square root of something that's being squared like that. Find f prime of x. Do you want to go through that, or do you know how to do that?
I just did the quotient rule on it. Yeah, I'm good.
So it's the bottom times the derivative of the top minus the top times the derivative of the bottom. All that looks great. X squared minus 4. Okay. There is some simplification of that. How much does she want you to do?
I don't know.
That is not fully simplified, and I'll show you why. Let's write out what we have here. X squared minus 4 to the 1/2 minus, if I multiply this out, I have x squared times x squared minus 4 to the minus 1/2. And then in the bottom, I have x squared minus 4. So I've got this in the top, this in the top, and this in the bottom. So at a very minimum, I can divide everything by x squared minus 4 to the 1.
Yeah.
Let's see how that's going to unfold. First of all, it might be easier to look at this doing it in 2 steps. Let's factor out from the numerator an x squared minus 4 to the minus 1/2. Okay? Now, what is that going to leave in the top? If I divide that by x squared minus 4 to the 1/2, I get x squared minus 4 to the 1 minus x squared, and when I divide that, I get 0. So that's the first step. Okay, so can you see that that is the same as what we started with?
Yeah.
Okay, now watch how this simplifies. This x squared minus 4 came from this, minus, this is just x squared. Okay, x squareds cancel. So I have in the numerator minus 4 times x squared minus 4 4 to the minus 1/2, all divided by x squared minus 4. So I can now simplify that, and I got minus 4 times x squared minus 4 to the minus 3/2, or minus 4 over x squared minus 4 to the 3/2. So it actually simplifies quite a bit when you go through all that algebra. Yeah. And that's always the algebra that's involved when you're taking quotient rules, is you are always going to have something in the numerator in two spots that looks just like your denominator. So we're always going to be able to factor a piece of this out and cancel it with that. All right. Let's blow this one up a little bit here.
That first question I had issues with.
Yeah, I have issues
in the end,
with it. I have issues with it also. Which of the following is false? Well, clearly A or B can't be the answer, right?
Yeah.
Because if A is false, then B would have to be true. Or they're both false. I mean, either they're both false or they're both true. So that can't be the right answer. So looking at C, the limit of f of x equals the limit of f of x as x goes to A. As x goes to A from the right has to equal the limit of f of x. Nah, okay, that doesn't have to be true, so that could be false.
That's why I picked that one.
Yeah, but I'm not sure it has to be false. D, certainly the limit does not have to equal f of A, so that could be false, but it could be true. E, the limit of f of x may or may not be equal to the limit of f of x, or the limit of f of x as x approaches A from the left may or not be equal to the limit of f of x as it approaches A from the right.
I guess E is more accurate than C.
Well, I don't know. Is E false?
I guess no, it's not.
I think E is true.
Yeah, I don't know. That question I had issues with.
I did too, to be honest with you. I don't really like this question, and there's one other on this section that I had issues with also. But let's not spend a whole lot of time on it. It might be a terminology question. I feel like you understand limits from the left and the right. I feel like I do also. So let's go on for the moment. Where is this not continuous?
When the bottom is equal to 0.
Right. And that is
X is 0.
Two places. Right? Isn't that when x is 0 or when x is 1? So when x can't be equal, x can't be equal to 0, x can't be equal to 1, and I don't think there's any other number where cubed is equal to the same thing squared. So I think that's the only two spots. So if I was laying out the domain here, I would say, well, it's continuous from minus infinity to 0, and from 0 to 1, and from 1 to infinity.
Yeah.
I don't see that answer on there, so
I should have answered E, none of these.
None of these is the only thing I can figure out. Yeah, because they don't put that 3 combination answer on there.
Really shouldn't have tried rushing as much as I did.
Okay. This one. There's only one number that x can't be, minus 9. Everything else makes it continuous. So A looks right. This is the one I had issues with.
Yeah.
B is true, at least that's what Wolfram Alpha told me. A, you can't approach x from the right side of 5. Right?
Yeah.
Because then you'd be taking the square root of a negative number. So A is not true. But on the other hand, if A isn't true, then D is true. It doesn't exist.
Yeah.
So I see D as being true. I see B as being definitely true. I see C as being true.
Yeah.
So I don't know what they want here. In other words, you can approach 5 from the left. If I graph this, let's graph it real quick. Back. Maybe it'll still have it in there. Yes. Notice the limit of the square root of 5 minus x as x goes to 5 is equal to 0. Here's the graph of it. The blue is ours. The orange is the imaginary part. You can approach this from the left. You cannot approach it from the right. But
yeah.
If B is true, why is D not also true? And C is also true. Certainly the limit of this function that we're looking at can be approached from the left. We can approach it from here, and we're approaching the limit of 0. So I got issues with that problem that probably aren't worth talking more about. Let's look at 5, because 5 is not right. To find the limit of something like this, the first thing you really should think of is just finding a common denominator and subtracting these two things. Okay, well, my common denominator is going to be 3 times x plus 3, right? And the top, this is going to be 3 minus the quantity x plus 3. So when I subtract those two fractions, this is what I get in full. Notice that that makes the top negative x over 3 times x plus 3, all divided by x. That's equal to negative 1 over 3 times x plus 3. Now we have it into a situation where we can plug in 0 for x, and we get minus 1 over 9.
Yeah.
That's the classical way to solve that. I suppose you could use L'Hopital's rule here. What would it be? It would be natural log of x plus 3 over 1. And when you plug in 0, that's the natural log of 3. Or, I don't know. I'm not sure I want to look at that with L'Hopital's rule. Although we certainly should be able to. We should be able to take the derivative of that. We should get the same answer. In other words, if we take the derivative of the top, we get natural log of x plus 3 minus 0. So natural log of x plus 3 over 1. And the natural log of x plus 3, when you evaluate it, is the natural log of 3. Is that minus 1/9? The natural log of 3? Well, this one puzzles me a little bit. Because I'm quite sure the way I did it is the correct way. What did you do here? Did you you tried to use the quotient rule to?
I guess that's what it looks like.
You got to be a little careful with L'Hopital's rule. First of all, you don't use the quotient rule on L'Hopital's rule. It's the derivative of the numerator divided by the derivative of the denominator. It's not the derivative of the quotient. Okay? But we don't need L'Hopital's rule here because I can get this to where once I combine those two fractions and divide top and bottom by x, I now have a function where when I substitute 0 for x, I don't get 0 over 0. And that's the whole key, is to be able to manipulate these functions so that you don't get 0 over 0. I'm going to have to look at this further on my own time to see why L'Hopital's rule doesn't give us that same answer. But I'm quite certain if I put that into Wolfram alpha, I would get minus 1/9.
Okay.
This one, you've got this one solved, correct?
Yeah.
This one, just going to take the derivative, which it looks like you've done properly, and then substitute 3 in. Looks like you've done that properly. Okay. This one.
Oh, what? I thought I finished did all that.
No, this one, C, is interesting problem. But first of all, let's look at A. What is the domain of F? Well, again, just like the radical, we can say that whatever is the argument of the natural log has to be greater than or equal to 0. So I can say that x over x minus 1 has to be greater than or equal to 0. And which means, wow. I multiply both sides by x minus 1, I get x is greater than 0, but it might be, or x is less than 0. I have to use a line chart on this. We've used line charts before, right?
I think so.
In other words, in order to solve that inequality, I have to use a line chart. And to use a line chart, I need to define my critical points. So my critical points are where the numerator is equal to 0 and where the denominator is equal to 0. Now I go to my line chart and I look to the left, in between, and to the right. Well, to the left of 0, negative divided by negative is a positive. It's going to be plus everywhere to the left of 0. In between, if I use 1/2, it's going to be negative. Any number between 0 and 1 gives me a negative quotient. And any number to the right of 1 gives me positive. So the domain of this thing is all x less than or equal to 0, so it would be negative infinity to 0 with a bracket combined with parentheses 1 to infinity. There's your domain right there. And it was not that easy to come up with without using a line chart. Solving inequalities of rational quotients is tough without using a line chart. As all you do is define your points that make the numerator 0 and the denominator 0, and then you test left, in between, and to the right of those points. And that will give you the solution to the inequality by just reading it. We're wanting wherever it's greater than 0, that means plus. Okay, so for the domain, that's the domain. Find the value of the derivative. Well, we know how to take.
I thought I had done what it looks like.
We know how to take the derivatives of
didn't.
this.
Yeah.
We can figure out how to take the derivative, substitute minus 1, and evaluate it. To take the derivative, you're going to take 1 over this argument times the derivative of the inside. And the derivative of the inside, we're going to have to apply the quotient rule, but it's not hard to do. Okay, so we can certainly do B. C is the one that's a little tricky. What's the normal way we find inverses? If I gave you a standard polynomial function, how would you find the inverse? Switch the variables and solve for y.
Oh, yeah.
Right.
I don't know, for some reason I just
No,
blanked it.
I knew you knew that. Well, that presents a little bit of a
I've
problem.
definitely done that before.
If I switch the variables here, now solving for y is a little tricky. How do we solve for y here? There's a little technique that it's not obvious if you haven't done it before, but I'm going to exponentiate both sides. I'm going to take this, make it the exponent of e, and I'm going to take this and make it the exponent of e. I'm allowed to do that. When they say you can do anything to the left side of the equation that you can do to the right, they mean it. You can do anything. You can take the integral, you can take the derivative, you can exponentiate it. You see what I've done here? I've just made the x the exponent of e, and I've made the natural log of y over y minus 1 the exponent of e. Well, now I have a rule for this. E raised to the natural log of some argument, that's equal to that argument. So that's equal to y over y minus 1. So now I'm there. Still not totally obvious how to solve for y, but basically going to solve it like we would any equation. I'm going to multiply e to the x times y minus e to the x times 1 equals y. Now what?
Solving for y.
How do I solve this? How do I solve this equation for y?
Would we factor out the e's on the left so that we could move the y's together?
No, we just multiplied them together, so we don't want to do that. That would reverse the step I just did. In other words, I multiplied y minus 1 times e to the x. So I don't want to factor it back out. That's going in the wrong direction. But what if I gather all my terms that have y in them? put everything else on the other side.
Okay.
Now I can factor out the y. And y ends up being equal to e to the x minus 1, and there's your inverse function. Actually, whenever you're trying to solve natural log equations, like the one I have circled here, think of that technique of raising both sides, making both sides the exponent of e. Because when you have e raised to the natural log of something, you can get rid of both the e and the natural log and turn it into that argument. So that's a cool technique. All right. Let's look at your second page here. Or any other part. We have about 20 minutes. Should we just go through these one by one? Test 2, 3, and 4?
Yeah, this is yeah, 2.
Okay. What is this statement saying? First of all, what does that mean? What does that mean right there that I have surrounded by that box?
That we're solving for what? That equation?
That is the definition of derivative.
Yeah. Yeah.
So that's telling us that the slope at 6 is minus 2. Since this gives us the slope of the function at 6, and they're saying it's minus 2. So f prime of 6 exists, yes. F of x is continuous at 6, yes, because otherwise its derivative would not exist. And f of 6 is less than 0. That we don't know for sure. Well, that's saying the function evaluated at
you're right.
0.
6.
Is all we know is that the slope is minus 2. The slope of the tangent line would be minus 2, but we don't know that f6 is less than 0. So I'd have to say 1 and 2 only here, B. Okay, to find where a function changes concavity, we are going to look for the inflection point. In other words, if I have a function like this, it changes concavity somewhere in there. It goes from concave down to concave up. And inflection points are where the second derivative is equal to 0. So if I take the second derivative of my function and set it equal to 0, that's my inflection point. So on this problem here, we want to take the second derivative of that, set it equal to 0, and that will be the value of x where my inflection point is, and then I can plug that value in to solve for f of a. So let's do that. Now let's see. F prime is equal to what?
3x squared minus 1, that turns into a 0, and then negative sine x.
Second derivative?
6x 0 plus cosine, or minus cosine x.
Yeah, you can't put these two negatives together to make them a positive.
Yeah.
In other words,
Yeah,
this doesn't disappear. It's just that when you take the derivative of minus 1, it's 0. You still have to take the derivative of minus sine x.
What I had done in my mind is I knew that negative sine x turned into cosine, so I saw the minus as the negative sign, and I didn't realize. I forgot that it was minus.
Okay, so now we're going to set this equal to 0. So really, the equation I have to solve is 6x equals cosine x. Now, you allowed, this is calculator test?
Yes.
Okay. How do you solve this equation? First of all.
6x.
Can you solve it without a calculator?
I don't know.
I don't know how to do it. What we have is a polynomial equal to a transcendental function. So I don't know how to solve this without a calculator, but with a calculator you just make one function y equals 6x, make the other function y equal cosine x, and find their intersection, and that's going to give you the solution. Let's see if Wolfram alpha will do it. 6x equals cosine x. X equals 0.1644.
Which is that one?
That one right there. And f of a would be whatever f of 0.164 is. Plugged into that equation right there. Not the second derivative. You're not going to plug in this answer into the second derivative to figure out f of a, because it didn't ask for f double prime of a. It asked for f of a. So all we did was we came up with an a, and now we're going to plug that a into that to come up with f of a. Oh, we don't even have to come up with f of a. It only asks for a. So, okay, good. Okay, so they gave us the derivative function. So where are we going to find a relative maximum? In other words, what are we going to do at this point?
Set that equal to 0?
Yeah. So 0 equals well, the only way 0 can be equal to the product of two things is if those things are equal to 0. So we're going to set this equal to 0, and we're going to set that equal to 0. Well, there is no value that will make e to the t over 7 equal 0. So we don't even have to worry about this. But this equaling 0 is the only thing we have to worry about. You see why? In other words, it's impossible for e to the t over 7 to be the thing that's equal to 0. So we have to solve this thing, or find the zeros of it. Let's put it into Wolfram alpha. And it'll give us the zeros. It's the the other beauty of Wolfram alpha. 3x to the third minus 13x squared plus 13x minus 3. Make sure I have the function correct. Okay. So there are zeros here, here, and here. And those zeros are 1/3, 1, and 3. Isn't that beautiful how they give you all the roots like that? So 1/3, 1, and 3, D. Good on that one?
Yeah.
By that I mean, are we good to go on?
Yeah, we're good.
Okay.
That one just looks like you have to take the time to solve it.
This one is a case of where we have the same highest, we have a x to the third in both the numerator and the denominator, and we're looking at end behavior. Well, end behavior is when x goes to either plus infinity or minus infinity. Well, if it goes to plus infinity, what would the limit be?
Plus infinity.
Yeah. In other words, we had another problem on your first test where it went to infinity and the limit was 3/6 because it had a 3x cubed in the numerator and a 6x cubed in the denominator, and x was going to infinity, so you just take the ratio of those coefficients.
Then it would be 1 for this one, right?
It would be 1/3. In other words, the coefficient.
Yeah, because there's a 3.
There's a 1 there and a 3 there. And we can ignore everything else. Whenever you're going to infinity, whether it's plus infinity or minus infinity, then it's the highest polynomial that matters only. The rest of these don't make a lick's worth of difference. So this is the same problem as what is the limit of x cubed over 3x cubed as x goes to negative infinity, still positive 1/3. Whether it's negative infinity or positive infinity. Notice that when you cube negative infinity, it still stays negative, so we're still going to have a negative over a negative to make it a positive 1/3.
Yeah.
All right. Okay, so what's the strategy here going to be for 5?
5? Just for which of the following, you would find what the, you take the derivative of the original function.
Okay.
And then find what the slope is at 2. So that you could write a tangent line, and then you'd see which one of those is the tangent.
So we know that f prime of x is equal to e to the x plus 2x, and we know that that's equal to 2. So the equation of that line, well, y is equal to mx plus b. Well, we know the slope is 2 at some point.
Where x is 2.
So it is some point that slope is 2. I got to think about this problem a moment. So e to the x plus 2x is the derivative function, and they're saying that it's equal to 2 at some point of x. Well, we have to solve this function for x. Then we'll be able to solve for b. Okay, so let me do this. Again, we have a polynomial equal to a transcendental. So the only way we're going to solve this is to say e to the x. Well, I guess I can just type it out. 2x equals 2. So we need to solve that for x. So that's going to give us the point. And that solution is that point right there. 0.31. How come it doesn't give me that solution? It's 0.31. It doesn't show me that number. I wonder why. Last time we did this, it showed me the number. All right, well, it doesn't matter. We can approximate that. That's about 0.315. Okay? So now we know that that slope is equal to 2 when x is 0.315. So I have to solve for b. What is y equal to? In other words, I can fill in 2 for the slope. I can fill in 3.12 for that, but in order to solve for b, I need a value for y. I guess I can plug in 0.315 into that. No. Into the original function to figure out what y is. There we go, and then that'll give us our equation. Let's see, the original function is e to the x plus x squared. So y is e to the 0.315 plus 0.315 squared equals my new y. In other words, that is f, that's equal to f of 3.15. So I can come up with a number for that. That's my y. I know what x is. I know what the slope is. I'll be able to solve for b. So let's do it. Let's see. E to the 0.315 plus 0.315 squared. E to the 0.315 plus 0.315 squared. And that is equal to my y. 1.469. So, in my original function, 1.47 equals, so the y, 1.47, equals the slope times the x, 0.315, plus b. Now I can solve for b, and I'm going to have my answer. B looks like it is, I'm going to subtract 0.63, so B looks like it's going to be 0.84. So y should be equal to 2x plus 0.84. That should be our equation. Let's see if it's one of our choices. Yep, C. That was a difficult one. I may have done it not the easiest way, but I don't know of an easier way to do it.
That's the way I would have done it.
Okay. Oh, I love problems like this. Actually, I don't. I hate them. 6 through 8. Differentiable functions f and g have the values shown in the table. F, when x is 0, f of x is 2, f prime of x is 1, capital G, okay. Is there a reason they used a capital G there? That should be a little g, right?
Yeah.
I mean, they used a little g up here, and they've used little f and f prime, so why didn't they use little g and g prime? That's all right.
Yeah.
We can work with that. If a equals f plus 2g, then a prime of 3. A equals f plus 2 times g.
I don't like this kind of problem.
What's that?
I've never liked this kind of problem.
No, I hate them. Although once you figure out what they're getting at, they're relatively easy to figure out. I've got to figure out what they're getting at here. F plus 2g. Well, if I go to the 3 and I do no, A prime would be F prime plus 2 times G prime? Do you have answers on these by chance? I hope so.
No, I don't. I don't have answers on this.
If we could get answers to one of them, we would know how to do all of them. I think I can say that A prime is equal to F prime plus 2, and I need the G prime there. In other words, I can't just drop that G. So if A prime is equal to F prime plus 2G prime, then A prime of 3 equals F prime of 3 plus 2G prime of 3. And from the table, F prime of 3 equals 4. Whoops, hold on. If I look at that table, F prime of 3 equals 4, plus 2, G prime of 3 equals minus 1, so the answer should be 2, which at least is one of the choices.
Yeah.
I actually think that is the right way to do it, maybe. Yeah. We'll do the next one exactly the same way. If B equals F times G, then what is B prime equal to?
F prime times G prime?
Well, F prime times G plus G prime times F, using the product rule. So now, B prime of 2 is going to be each of these, F prime of 2 times G of 2 plus G prime of 2 times F of 2. We get each of those from the table. What's F prime of 2?
F prime of 2 is 3.
So 3 times G of 2.
1.
Plus G prime of 2.
Negative 2.
Times F of 2.
5.
So that would be 3 minus 10 minus 7. If that's not on there, we're probably doing it wrong. If it's on there, we're probably doing it right. It's on there.
Okay.
Okay?
Yeah.
What's D prime if D is equal to 1 over G?
D is 1 over G, then
D prime is 1.
Use the quotient, wouldn't we? Well, can we just let the 1 drop? Go 0 over G.
Yeah, no, we just used the quotient rule. What was I thinking? I was thinking, for some reason I was thinking natural log. It's minus 1 over G squared. Right?
Yeah.
Because it would be G to the minus 1, so it'd be minus 1 to the G to the minus 2. Okay, so D of 1 is going to be minus 1 of G of 1 squared. G of 1 is 3, so it would be minus 1/9. C. Alright, I just realized that we're over here. So maybe we can pick up next time.
Yeah.
Yeah,
Thank you.
This is a fairly, these are tough questions. But some of those questions on that first one bother me a lot. I think he may not have allowed for multiple truisms when he said which of the following is true. I don't know. Not sure. But anyway, you have a good week, and I will talk to you next Saturday.
You too.
All right, Chase. Bye-bye.